One of simulation's key uses is process optimization, and Moldex3D has two different ways of optimizing your molding condition through a design of experiments method. The expert function enables the traditional Taguchi method, while the new AI optimization wizard in Moldex3D 2025 enables easy optimization of processing windows using an AI kernel. My name's Alex Baker, and welcome to another advanced module breakdown. In Moldex3D 2025, we've introduced a new function called the AI Optimization Wizard, and this enables you to use an approach that utilizes an AI kernel to run these simulations automatically without the need for a rigid structure like a Taguchi array. To find the AI Optimization Wizard, you're going to right-click on the run you want to base on, you'll go to the Optimization, and then you'll click AI Optimization Wizard. In the AI Optimization Wizard, you're going to specify two things primarily. The first one is your control factor, which is what you're looking to vary for these analyses. These control factors for the AI Optimization Wizard are currently limited to just processing conditions, making this more of a process optimization sort of approach. We can see filling time, melt temperature, packing time, cooling time. You can see a bunch of options under this dropdown, and you can choose as many of those as you want to. You can see I can choose multiple control factors, such as filling time and melt temperature. Over on the right side is how much I want to vary these. Now, the middle of the range that shows up is going to be from the base run that you right-clicked on originally. You can change these extents. Let's say I want to vary between 1.5 and 2.5 seconds. And then for melt temperature, let's say I go a little bit wider. Let's say I go from 275 to 325. Okay, so we have our variables set up. Now, what do we actually want to optimize for? That's what the quality factor is meant to represent. I'm going to click on the dropdown for quality factor, and you can see a list of result items under this dropdown. There are many things that you could want to optimize for. For example, uniformity of volumetric shrinkage, part weight, sprue pressure, clamp tonnage, warpage. You can choose as many quality factors as you want. Each quality factor will have a designated default goal assigned to it. For example, with warpage, I want it to be as small as possible. For volumetric shrinkage, for example, I want this to be as uniform as possible. And you can weight these appropriately. So if, for example, I have warpage and packing volumetric shrinkage, but I know that warpage is a little bit more important to this optimization, I can make the warpage, let's say, 5 times as important as the volumetric shrinkage. For this study, I'm just going to get rid of volumetric shrinkage, and we're going to look at warpage specifically. Down below, you can add a constraint, which tells us that some value of our results has to be constrained to a certain range. If we have a tolerance that we can't exceed, then we can set that here. So for example, the part weight must be greater than 150 grams, for example. This is an optional value, and so you do not have to apply constraints, but they are used for the deterministic method that the AI optimization kernel utilizes. The last thing to set is the number of maximum iterations. Most of the time, the AI kernel will be using all of these iterations to run the analysis to achieve a reasonable minimum target based on the range that you specified. If I specify, let's say 10 maximum iterations, I can hit create, and you can see that it has created a new AI optimization for me, and I can review that AI optimization input screen at any time I want to through the AI optimization info. I can just double click on that to bring that window up. This AI optimization took about 22 hours to run. The mesh element count here is about 250,000 elements for the part. And so this is somewhere in the realm of what you could expect for the settings that I showed earlier. The output from the AI optimization wizard is just going to be a singular run, unlike the typical DOE where you get several runs from the Taguchi array. For the AI optimization wizard, it will only give you the final run that represents the entirety of the AI optimization path. The first thing I can open up is the AI optimization info screen. Like I just mentioned, you can double click on the AI optimization window to see the inputs for this analysis. Once the AI optimization is done, you'll also have a new tab over on the right here for summary, where it will tell you all of the iterations that it went through and the result of each of those iterations. This AI optimization did utilize all 10 iterations, and so we can see as it went through the variation of the range that we gave it, we can see as it started to vary those, it started to hone in on where the optimal process condition was, and it highlighted the optimal process condition as 100% score, which is what the AI kernel uses to qualify whether this iteration was good or not. And that ends up being our optimized process condition. So we can see that the filling time closest to the maximum and the melt temperature closest to the minimum gives us the lowest amount of warpage in this case. This is the primary information that we are looking for from the AI optimization wizard. There's also one other item that it outputs that could be of use. That is called the parallel coordinates plot. This also shows in the typical DOE structure. And the parallel coordinates plot for the AI optimization tool gives us each of the iterations. And over on the right side, we see the total displacement scale. And so the iterations that had the lowest displacement will show as blue. The iterations that had the highest displacement will show as red, giving us a visual indication of what process conditions are optimal in this case. This is pretty much just a visual interpretation of the table we just looked at. So we can see that as the filling time goes higher, the warpage decreases. You can see a bunch of these blue lines around the 2.5 or around the upper limit of that filling time range that we gave. And then to the right of that is the melt temperature. We can see that pretty much all these blue lines are converging on that minimum of the range that we specified. So it might be best to even go a little bit lower than 275 for this case to minimize the amount of warpage that we get. Unlike the typical DOE structure, this is not an active parallel coordinates plot, meaning I can't drag these up and down. However, if I do drag across a series of lines, it will highlight those lines so that I can isolate those from the rest of the graph. Especially in large DOE sequences, it's very typical that these graphs get very busy, and so being able to isolate a certain number of curves is definitely beneficial. Down below the parallel coordinates plot, we get the control factor iteration curve, which just tells us how many iterations it went through and the path that it went as it progressed through this AI optimization approach. It has one of these for filling time and also one of these for melt temperature. Below that is the quality factor iteration curve, and so it tells us as we go through our number of iterations, how the displacement was gradually decreasing as the AI kernel hones in on those optimized process conditions. In addition to all of these, it does output the simulation results that are associated with the optimized run. And so you can utilize those however you'd like to, as though they were a normal simulation output. The standard DOE function has been available in Moldex3D for several years, and you can access this function by going under the run that you wish to iterate upon, right-click, optimization, and DOE Wizard. In previous versions, the DOE Wizard was its own option. In 2025, this is an arrow over to the DOE Wizard. When you're using the DOE Wizard, you're going to use a Taguchi type method to see which combination of those control factors is the best for the specified quality factor. Under the levels dropdown, this is how many different items in each control factor you're looking to vary. You can vary the number of control factors, and then you can choose your Taguchi array if there are multiple available to you. Below this is your control factor selection. If I click on the dropdown, I'll see a bunch of items here. You see a lot of different processing conditions, but you can also use different materials and meshes for these studies as well. For example, if I set up multiple gate locations, or if I want to try to out different materials, I can use the DOE wizard to indicate which of these materials or which of those gate locations is most suitable with respect to the specified output. In this case, let's say we do a filling time study, and let's say we do a melt temperature study. I'm going to increase the number of levels to 3 so that I can test a few different values within a specified range. Let's say I go from 1.5 seconds all the way up to 2.5 seconds. For melt temperature, let's say we do 275, and then just going up linearly to 325. These are the different values that this Taguchi array is going to test. And you can see that it's going to create 9 runs as a result. And what it's going to try to optimize is the quality factor. The quality factor is what we're looking to optimize. And so this could be something like warpage, or this could be sprue pressure, or clamp tonnage, or part weight. All of these sorts of optimizations are possible in the DOE function. Here, I'm going to specify warpage. And by default, the DOE wizard has already specified that we want the warpage to be as small as possible. You can continue adding quality factors with different weightings assigned to them, similar to the AI optimization wizard. If you click next, you'll see all of the permutations and all the different combinations that it's going to test. And then at the end, it will give you the optimized output, which I've already ran. You can actually see in the background here, this is that exact Taguchi array. And I can click on the DOE info to see the setup of this DOE. Once the analysis is ran, once all of these simulations are ran, now when you run a DOE, these runs are independent of one another. So these will quite literally log in sequence with one another. They'll run one after another. And so it may take some time for this DOE to complete. We can see runs 1 through 9 are created, and you'll be able to see all of the results for those independently. And then it also creates the optimized run at the end to tell us which of those permutations was optimal for warpage in this case. The DOE info has a summary tab. We just saw the summary to kind of see a breakdown of what was going to run. But now that the DOE is finished, now we can see the results of that DOE. Now it's only going to test the values that we put in. And so there is no interpolation between these different values from the Taguchi array itself. But we can see that run 9's output as run 12. Those are basically just copies of one another. And we can actually see that the value that it arrived at is actually the same as what we got from the AI optimization tool. If we remember, 2.5 and 275 degrees Celsius. If we go back to the AI optimization wizard, the optimization found 2.5 and 275 to be the optimal properties. So as low of a melt temperature as possible and as slow of a filling speed as possible. And so these two methods end up agreeing with one another, making both of them just as viable. Now, something that we get in the standard DOE that we don't get in the AI optimization tool is an interactable parallel coordinates plot. The parallel coordinates plot shows us the trendwise information, showing us the run number, the control factors, and the ultimate quality factor over here on the right. In the standard DOE, starting in 2025, we're able to click and drag these parallel coordinates numbers to see what a live reaction would be on the final quality factors. I can move each of these independent of one another to see the relative impact. Like we can see here, the melt temperature seems to have a much bigger impact on warpage than the filling time does. You can actually see that there's even an optimization point where it kind of the warpage increases, and then at some point when the filling time gets low enough, now the warpage starts decreasing. So there might actually be a value a little bit further down below 1.5 where the warpage actually becomes a lower number than what we predicted through this DOE. This sort of information is extremely valuable and can be used going forward if we were to do a separate DOE or if we were to start optimizing for some other variables. In addition to the parallel coordinates plot, the standard DOE also gives us a couple of additional items. The first one is the quality response, telling us how the quality factor responded to the different control factor variations. All right, so we can see for filling time here, we have 1.5, 2, and 2.5. And then we have the melt temperature, 275, 300, 325. This gives us a really good visual representation of which of these factors is more sensitive to the quality factor that we have selected. In this case, because the melt temperature ended up varying quite a bit more, I can say that the melt temperature is more sensitive to the warpage than the filling time is, although both of them seem to have some sort of impact. From a statistical sense, we also have the S&N ratio response, which you can derive similar information from. The definition is slightly different, but the intended information is the same. You also get a response surface, which shows you the representation of that sensitivity on a three-dimensional scale, with both of those control factors showing in addition to the selected quality factor. I can choose different control factors here. If I did more than two, then I could choose those to represent this graph a little bit differently. In this case, I only have two, and so I can only represent this graph in one way. Thank you for watching this advanced module breakdown, and next week we'll be tackling the ever popular topic of warpage through a root cause analysis, breaking down the different causes of warpage and figuring out much more clearly where improvements can be made in the model, material, and process. Let us know down below what topics you'd like to see covered in the future, and we'll see you in the next one.